3,000 miles below your feet, Earth's iron core has changed direction. The planet is now spinning faster than at any point in recorded history. The magnetic North Pole is sprinting toward Russia, and the Atlantic current that keeps 3 continents warm is showing precursor signals of collapse. These are confirmed, measured facts. In this video, we follow one chain of events that started at the center of the Earth and climbed upward through every layer of the planet. The magnetic field is breaking down. The axis is shifting. The ozone layer is under attack from 2 new directions, and there is a timekeeping crisis with a hard deadline. If you want more videos like this, subscribe and hit like. Let's begin. 3,000 miles below your feet. Something changed. You didn't feel it. No instrument on the surface registered a tremor, no sensor threw an alert, and the people who eventually found the evidence spent years checking their data before they said anything out loud. But the change was real. It was consequential, and it had been quietly underway since roughly 2010. At the very center of this planet sits a solid ball of iron and nickel, approximately the size of the Moon, suspended inside a vast ocean of liquid metal called the outer core. It spins. For most of the 20th century, that inner ball was outpacing the planet around it, rotating slightly faster than the surface you walk on. Scientists called this superrotation, and they had largely assumed it was the natural state of things. It wasn't. Around 2010, the inner core began to break. By the time a landmark study confirmed it in 2024, the data told a clear story. The inner core is now lagging behind the crust above it, spinning slower than the planet it sits inside. The planetary heart has fallen out of sync. The deepest humans have ever drilled into the crust is a little over 7 miles, a Soviet borehole in Russia that took more than 20 years to complete. The inner core is 3,200 miles down. We have never come close to touching it, cannot see it. The only reason we know it exists is because of what it does to the waves that pass through it. When a large earthquake fires energy through the planet, that energy travels in waves. Some of those waves pass straight through the deep interior, bending and slowing depending on what they move through. Scientists compare those wave signatures against what the physics predicts, and from the differences, they build a picture of what's down there. For decades, that picture showed a solid iron sphere spinning slightly ahead of the rest of the world. Then the picture changed. John Ridddle and his team at the University of Southern California analyzed decades of seismic recordings and found the reversal with unusual clarity. The superrotation had ended. The inner core was now subrotating, falling behind the surface above it. This was likely a cycle. Evidence suggests the core oscillates on periods of roughly 70 years, breaking and then spinning up again over generations. It may have happened many times in centuries past, in eras before any instrument existed to record it. But here is the thing that matters for everything that follows. The inner core doesn't exist in isolation. It sits inside the liquid outer core, which churns constantly and generates Earth's magnetic field. The two are coupled by electromagnetic forces and gravitational torques, locked in a constant exchange of energy. The outer core is coupled to the mantle above it, and the mantle is coupled to the crust. When the inner core breaks, that rotational energy doesn't vanish. It transfers upward through the planet, layer by layer, all the way to the surface. The core slowed. Hold on to that fact, because nothing that comes after makes sense without it. Listening is the only tool available. There is no drill that reaches the inner core, no probe that can descend 3,000 miles through rock and liquid metal, no instrument that can directly image the boundary between the solid sphere at the center and the molten ocean surrounding it. What scientists have instead is sound, planetary-scale sound in the form of seismic waves, and the extraordinary patience to compare recordings across decades. The technique that revealed the inner core's behavioral change relies on what researchers call doublet earthquakes. and the idea behind it has a quiet elegance. Every so often, two earthquakes strike from the exact same location, years or even decades apart, same fault, same depth, same geometry of the rupture. In theory, a pair like this should produce nearly identical seismic wave signatures. The energy leaves the same spot, travels through the same planet, and arrives at sensors worldwide in the same pattern. But if the inner core has rotated to a different position between the two events, the waves that pass through it will arrive slightly differently. They will have traveled a fractionally different path through a fractionally different slice of iron. That tiny difference, measurable in fractions of a second at sensors thousands of miles away, is enough to calculate exactly how far the inner core has turned. The planet's inaccessible center, revealed by its own echoes. Researchers assembled a remarkable archive of these twin events, drawing heavily on recordings from the South Sandwich Islands in the South Atlantic, a volcanic chain that generates doublet earthquakes with unusual regularity. The dataset spans 32 years. Some of the oldest reference points in it come from Soviet nuclear tests conducted in the 1970s and 80s. Those detonations, set off deep in the Cold War for reasons that had nothing to do with geophysics, produced clean, precisely timed seismic pulses that became ghost snapshots of where the inner core was sitting decades ago. Weapons tests from a vanished superpower are now some of the most valuable data points in the study of Earth's deep interior. 121 repeating earthquake pairs, combined with the archived test records, gave the team a timeline spanning half a century. Laid out in sequence, the waveform shifts told a coherent story. The inner core had been gaining on the surface throughout most of the 20th century. Then it began slowing around 2010, and now it runs behind. What makes this detection method remarkable beyond its elegance is its sensitivity. The inner core is moving at a rate measured in fractions of a degree per year, roughly comparable to the crawl of a minute hand on a clock, and yet the seismic technique is sensitive enough to detect it from the surface. A structure 3,000 miles underground, invisible and unreachable, betrayed by the way it bends a wave. That precision created a problem. Once the tool was sensitive enough to detect the slowdown, it was sensitive enough to detect everything else the inner core was doing. And when the team looked more carefully, they found something in the data that no existing model had predicted, something that turned the story from strange into genuinely unsettling. The method could detect the planet's core twitching, which made what came next unavoidable. Throughout most of the 20th century, the story of Earth's inner core was relatively straightforward. The solid iron sphere at the center was spinning slightly faster than the planet around it, gaining roughly a degree on the surface per year, and this superrotation was considered a stable and probably permanent feature of Earth's deep interior. Textbooks described it. Models were built around it. The assumption held for decades. The first hints of a reversal appeared in the data around 2009 and 2010, but they were subtle enough to explain away. Measurement noise, researchers suggested. Limitations of the seismic archive. The signature of a single unusual earthquake pair distorting the picture. Alternative explanations circulated for years, and the debate in the literature was genuine. Multiple teams published competing analyses pointing in different directions. The inner core, it turned out, is a difficult thing to reach consensus about. More data, more doublet pairs, more years of recordings from more seismic networks, all pointing the same way. By 2023, the pattern was hard to dismiss, and the 2024 study in the journal Nature made it definitive. The inner core is now subrotating. It has been slowing for over a decade, and it is currently lagging behind the crust by a measurable and growing margin. It is worth pausing here to be honest about what this means and what it doesn't. The inner core's shift from superrotation to subrotation is almost certainly cyclical. The physics of the coupled core mantle system suggest oscillations on roughly 70-year timescales, driven by the push and pull of electromagnetic forces and fluid dynamics in the outer core. This particular oscillation has probably happened before. The planet has not suddenly broken. The inner core slowing down is, in a geological sense, normal behavior. But here is the wrinkle that makes the timing matter. This normal behavior is happening right now, inside a planet whose surface systems are under simultaneous and compounding pressures that have no historical precedent in the era of measurement. A 70-year cycle that might have passed unnoticed in an earlier century is happening at the same moment that the magnetic field is weakening. The poles are accelerating, the oceans are reorganizing, and the axis is shifting. The cycle itself may be ordinary. The context around it is anything but. Consider what the confirmation of the slowdown actually required. Seismologists needed decades of seismic archives, Cold War nuclear test recordings, and a dataset of over 100 repeating earthquakes from one of the most remote volcanic chains on Earth. That is how long it takes to build a case against a planetary structure you cannot observe directly. And the implication cuts two ways. The seismic record before the 1970s is sparse, meaning there could have been earlier oscillations in the inner core's rotation that we never detected, never had the instruments to see. The slowdown was confirmed only because the tools finally existed to confirm it. How many previous oscillations happened in silence, in centuries, when nobody was listening? And then, in early 2025, a follow-up study arrived that changed the shape of the question entirely. It was doing something else simultaneously, something that the original superrotation debate had completely missed. A slowing core would have been strange enough, but the follow-up study landed, and the story got stranger. February of 2025 brought a paper in the journal Nature Geoscience that rewrote the standard model of Earth's inner core in a single sentence. The sentence came from Guaning Pang, a geophysicist at Cornell University and a co-author of the study, and it read, "The surface of the inner core is soft, maybe as soft as jelly." Read that again. The object at the absolute center of this planet, the solid iron sphere that planetary science had treated as a rigid anchor point for decades, has an outer surface that is deforming, not slowly solidifying the way a textbook cooling model would predict. Deforming. Moving in ways that the researchers, by their own admission, still don't fully understand. The mechanism involves the boundary layer between the solid inner core and the liquid outer core, a region that was previously assumed to be sharp and relatively stable. The new study found it is neither. Iron is crystallizing out of the liquid in some places and melting back into it in others, and the pattern of this crystallization and dissolution is uneven, asymmetric, and actively shifting. The outermost surface of the inner core is essentially a dynamic landscape, solidifying in some regions and liquefying in others on timescales that are geologically fast. The asymmetry matters. If the inner core were deforming symmetrically, the mass redistribution would cancel out and the effects on rotation would be minimal. The problem is, the deformation appears to be concentrated, with certain sectors of the boundary actively changing while others remain more stable. An asymmetric mass shift inside a rotating body produces a torque. That torque has to be absorbed somewhere else in the system. The outer core's churning dynamics respond to this. The mantle above it responds to that. And the crust that everything rests on responds to the mantle. What the lead researcher John Vidali said in describing the finding captures the texture of the discovery well. The inner core's surface is moving around in ways we hadn't detected and still don't understand very well. That phrase, "still don't understand very well," is doing a lot of work in the context of this video. Scientists don't say things like that lightly. These are researchers who specialize in the deep interior of a planet, who have spent careers building models of how the core behaves. When they say the behavior is detected but unexplained, the honest response is to take that seriously. There is a physics consequence to a shape-shifting inner core that extends far beyond the abstract question of what the core looks like. Mass distribution matters in a rotating body. When the distribution of mass changes, even subtly, the rotation of the system adjusts to compensate. A figure skater extending one arm while keeping the other tucked shifts the axis of their spin slightly. The same principle applies to a planet. If the inner core is redistributing mass at its boundary, and if the outer core's churning dynamics are responding to that redistribution, the effects propagate. They climb upward through the mantle, through the crust, all the way to the surface. The solid core was shape-shifting, and when mass redistributes inside a rotating body, physics demands that something compensate. That compensation was already happening, on the very surface you're standing on, and had been for years before anyone identified its source. Physics makes a demand that has no exceptions. In a closed system, angular momentum is conserved. It cannot be created, destroyed, or simply lost. It transfers. When one part of the system slows, another part speeds up to absorb what was released. This rule governs spinning tops, gyroscopes, collapsing stars, and the interior of this planet with equal indifference to human expectation. Inside Earth, the mechanism that carries momentum between the inner and outer core involves two forces working in tandem. Electromagnetic coupling links the two regions through the magnetic field lines that thread both the solid sphere and the liquid ocean surrounding it. Gravitational torques between the slightly asymmetric inner core and the mantle above provide a second channel of exchange. These connections mean the inner and outer core are not independent objects. They are parts of one dynamic system, exchanging spin energy on timescales ranging from years to decades. When the inner core began decelerating around 2010, that rotational energy moved into the liquid outer core. The outer core, in turn, transferred some of it further outward into the mantle, and from the mantle into the crust. The surface of Earth, imperceptibly but measurably, began to absorb the momentum the core had shed. Think of it this way. A figure skater, spinning with arms extended, suddenly pulls them in tight. The spin accelerates. Now reverse the image. A skater spinning fast releases their arms outward, and the spin slows. Earth's inner core is the arms, in a sense. When the core shed angular momentum outward, the outer regions of the planet received it. The crust and everything on it began moving fractionally faster. The word fractionally is doing important work there. We are talking about a change in the length of a day measured in milliseconds, far below the threshold of human perception, far below the threshold of most instruments. A millisecond is 1,000th of a second. The change in the length of a day is smaller than the time it takes to blink, and yet it is real, it is measurable, and it has been accelerating. Scientists tracking Earth's rotation using atomic clocks, which can measure time to a precision that makes ordinary clocks look medieval, began noticing the trend in the early 2020s. Day lengths were shortening. Fractionally, consistently, record after record was being quietly broken. The coupling is worth understanding in a little more depth because it reveals how thoroughly connected the deep interior and the surface actually are. The liquid outer core churns in complex, turbulent patterns driven by heat, by the rotation of the planet, and by the gravitational influence of the solid inner core beneath it. When the inner core's spin changed, the turbulent patterns in the liquid above it shifted in response. The altered flow changed the electromagnetic drag between the outer core and the mantle sitting above. And the mantle, which makes up the vast majority of Earth's volume, transferred the energy shift to the thin shell of crust we live on. A change in an iron ball that no human has ever seen, 3,000 miles underground, arrived at the surface as a fractionally shorter day. The planet is one continuous machine, and its parts do not change independently. The planet is spinning faster. That sounds abstract, and the consequences already have a deadline, July 5th, 2024. Earth completed its rotation 1.5 milliseconds faster than 24 hours, the shortest day ever recorded since atomic timekeeping began in 1973. The previous record had been set in 2020. Before that, the record-breaking days had been clustered in 2020 as well. Multiple days across 2025 approached the mark. These are consistent readings from atomic clocks maintained by timing labs around the world, cross-checked against each other and against astronomical observations of Earth's position relative to distant stars. The trend is not a fluke. Since roughly 2020, Earth has been rotating faster than at any comparable period in the 50-year history of precise atomic timekeeping. And the departure from historical baseline is accelerating, not stabilizing. Scientists are careful about causation here because Earth's rotation is influenced by many things simultaneously: atmospheric pressure changes, ocean current shifts, seasonal redistribution of snow and water, and the deep interior dynamics described in the chapters before this one. Isolating each contribution is genuinely difficult, but the consensus view among researchers who study Earth's rotation is that the liquid outer core, reducing its own angular velocity, transferring momentum upward through the mantle and into the crust, is the dominant driver of the long-term acceleration. The deep interior is producing a signal that is now detectable in the length of your day. There is a way to feel the scale of this. Every year, Earth takes slightly longer to travel around the central star of this solar system because the star's gravitational pull is gradually drawing the planet infinitesimally outward over geological time. The year is getting longer at a rate so slow it is barely worth mentioning across a human lifetime. But the day, the planet's own rotation, is going in the opposite direction right now, shortening by fractions of a millisecond per year, driven from the inside. Here is a useful frame. The last time Earth's rotation was reliably measured before the atomic clock era, the tools were pendulum clocks and astronomical observations. Astronomers used the position of stars to tell time, tracking when they crossed the meridian each night. The method was precise enough to catch the drift in Earth's rotation, but only over years and decades. The modern era of atomic timekeeping, which began in 1973, created something unprecedented: the ability to measure every single day in real time against a perfect standard, with enough precision to catch changes accumulating over months rather than decades. The records being broken in 2020, 2024, and 2025 exist only because the measuring instruments are now good enough to see them. And what they see is a planet that has quietly sped up over the past 5 years in a way that the instruments we built civilization around were never designed to track. We built a global timekeeping system on the assumption that Earth's rotation was slowing slightly over time, a system designed to handle that gentle, predictable drift. The drift has reversed. And the timekeeping system, which underpins the functioning of the global internet, satellite navigation, financial transaction timestamps, and network synchronization protocols, was designed for a planet that was supposed to stay roughly predictable. A shorter day might sound like a cosmetic problem, the kind of thing that matters to astronomers and almost nobody else. It isn't. And the reason it isn't leads to something that the engineers who built the internet's time infrastructure are deeply uncomfortable discussing. Since 1972, global timekeeping has been maintained through a system called Coordinated Universal Time, which is designed to stay aligned with Earth's actual rotation, while also matching the perfect precision of atomic clocks. These two standards, astronomical time and atomic time, drift apart because Earth's rotation is irregular and atomic clocks are not. The solution agreed upon in the 1970s was simple. When the gap between them grew too large, add a second to the official clock. Press pause on global time for 1 second, let Earth's rotation catch up, then continue. This has been done 27 times between 1972 and the present. Each added second is called a leap second, and each one has been positive, meaning a second was inserted into the clock. The system assumed Earth was slowly breaking over time, which it had been for most of modern history, and that the correction would always be the same kind of correction, adding time, never removing it. Earth is now going the other direction. The planet is spinning too fast, meaning atomic time is falling behind astronomical time rather than running ahead of it. At some point, a second will need to be removed from the global clock rather than added. Geophysicist Duncan Agnew of the Scripps Institution of Oceanography, who published on this problem in the journal Nature in 2024, placed the likely date for this correction at around 2029. The problem is that removing a second has never been done. A positive leap second is disruptive enough, requiring every computer system that maintains precise timestamps to handle a minute that contains 61 seconds. Going from 11:59 and 59 seconds directly backward to 11:59 and 58 seconds, on the other hand. Researchers at Northeastern University, comparing it to the year 2000 computing crisis, described a negative leap second as essentially on par with that concern. Computers can accept time standing still for 1 second. Having time run backward, even by 1 second, is a different kind of problem. Financial systems executing millions of transactions per second, GPS satellites transmitting position data synchronized to thousandths of a second, network protocols that assume timestamps always increase. All of these would be affected. 1 second. That is the entire problem. The planet is spinning fast enough to require 1 second be subtracted from global civil time, and doing so has never been attempted. The practical stakes are easier to feel with a concrete example. The global financial system executes trades time-stamped to microseconds, and the order in which those timestamps fall determines the legal priority of competing transactions. A moment when official time briefly runs backward, when 11:59 and 59 becomes 11:59 and 58 before proceeding to midnight, would create a window where the order of time-stamped events becomes ambiguous. Engineers at trading firms, internet infrastructure companies, and telecommunications providers have been quietly dreading this for years. The problem has a fix. Eliminate leap seconds entirely and let astronomical and atomic time gradually drift apart. Several major tech companies have been lobbying for exactly this. But the timeline for any international agreement is long, and 2029 is not. And then it gets stranger. The reason the deadline hasn't already arrived, the reason we have until 2029 rather than 2026, involves something completely unrelated to anything inside the planet, something cold, something melting. Here is the sentence that deserves its own moment of silence. Global warming is currently protecting the global timekeeping system from a computing crisis. Sit with that. The planetary process most commonly described as the defining threat of this century is, at this precise moment in history, acting as a brake on a different problem caused by a completely separate planetary process. The world is structured more strangely than anyone's mental model of it tends to accommodate. The two phenomena are entirely independent in origin. The inner core slowing down has nothing to do with greenhouse gases or industrialization. It is a geological cycle rooted in the electromagnetic physics of liquid iron, running on a timescale that spans human generations. Global warming, by contrast, is a surface phenomenon driven by atmospheric chemistry, running on a timescale of decades. These two things have no common cause, and yet they have collided in the most unexpected way. One is accelerating the planet's spin, the other is breaking it, and the net result determines when a global computing system needs an intervention it was never designed to handle. The fact that we can even measure this interaction, that we can trace the angular momentum contribution of Greenland's melting ice sheets and weigh it against the momentum shift rising from 3,000 miles underground, is itself extraordinary. 40 years ago, we didn't have the instruments to see either signal. Now we can see both, simultaneously, working against each other. The mechanism is straightforward once you understand angular momentum redistribution. As Greenland and Antarctic ice melts, the water released flows toward the equator, distributing along coastlines and into ocean basins. Water near the equator is farther from the planet's rotational axis than water locked up in polar ice sheets. When mass moves outward from the axis in a spinning system, the system slows. Like a figure skater extending their arms, Earth becomes slightly more oblate as equatorial water increases, and the spin rate decreases to compensate. Geophysicist Duncan Agnew calculated that without this braking effect from ice melt, a negative leap second would have been necessary as early as 2026. The redistribution of meltwater bought the timekeeping system 3 additional years, 2029 instead of 2026. The same process doing this is, of course, injecting enormous quantities of fresh water into the North Atlantic, threatening to disrupt the ocean circulation system that keeps northern Europe livable and regulates monsoon rainfall across 3 continents. Ice melt is simultaneously delaying a computing crisis and accelerating an oceanographic one. The planet's systems are not parallel stories. They are a single tangled story. There is one more layer to the irony. The ice melt that is slowing the rotation will eventually stop providing this cover. If the rotation continues to accelerate, driven by the deep interior dynamics discussed earlier, the meltwater break will at some point be insufficient to offset it. The window of protection is temporary. The computing crisis is delayed, not resolved. The ocean is doing 2 things simultaneously, slowing the spin from above while flooding the Atlantic from below. And the Atlantic has its own crisis underway, one that begins at a depth most people never think about. In a layer of the ocean where the water moves with the patience of centuries, between Africa and South America, there is a region where the invisible fabric that protects everything on Earth's surface has frayed almost completely. Earth's magnetic field, which normally registers around 50,000 units of magnetic intensity at the surface, drops to roughly 22,000 in the heart of this region, less than half the global average. Satellites passing through it experience elevated radiation exposure. The Hubble Space Telescope routinely shuts down sensitive instruments when its orbit carries it across this zone. Astronauts aboard the International Space Station see more frequent light flashes caused by cosmic ray particles hitting the retina when they pass over it. This is the South Atlantic anomaly, and it has been growing. The cause lies deep beneath the region, at the boundary between the liquid outer core and the solid mantle. In most of the planet, magnetic field lines generated by the churning iron in the outer core project outward, away from the center of Earth, rising through the mantle and the crust to provide the protective field that deflects solar wind and cosmic radiation. In the South Atlantic region, something is different. The field lines beneath it are looping inward, back toward the core, instead of projecting outward. These are called reverse flux patches, and they create a zone where the outward-facing field is dramatically weakened. In 2025, data from the European Space Agency's Swarm satellite constellation, analyzed by a team led by Professor Chris Finlay at the Technical University of Denmark, confirmed that the anomaly expanded 8% in a single year. The African edge of the anomaly is weakening fastest, driven by a reverse flux patch migrating westward from beneath the continent, growing as it moves. Between 2019 and 2024, the most rapidly weakening region lost over 400 units of magnetic intensity in 5 years. The overall global magnetic field has lost roughly 10% of its strength over the past 200 years, with the rate of decline appearing to increase in the recent decades. 780,000 years have passed since the last full polarity reversal, when the magnetic north and south poles swapped positions entirely. The average interval between reversals over geological history is around 250,000 years. The arithmetic alone is arresting. Scientists are careful to note that the anomaly does not mean a reversal is imminent. Reversals unfold over thousands of years, and the geological record contains no evidence linking them to mass extinctions or catastrophic surface conditions. The anomaly is a structural feature of the core dynamics and has probably recurred periodically over millions of years. But here is what the data shows right now. The field is at its weakest measured point in the modern era, and it is continuing to weaken in the place where it is already weakest. The anomaly grew 8% in a single year. Extrapolate that trajectory forward, even conservatively, and the affected zone in 2 decades covers a vastly larger swath of the sky above the South Atlantic, sending more radiation to more satellites, more aircraft electronics, more ground infrastructure in more countries. The 8% figure is a measurement, not a forecast. The trajectory beyond it is what keeps researchers uneasy, and the anomaly is a symptom of something moving in the same system that caused the core's slowdown. The outer core is reorganizing, and there is another way that reorganization is showing up, one that becomes visible when you look not at the field's strength, but at its direction. Racing is the only word that fits what Earth's north magnetic pole has been doing for roughly the past 30 years. For centuries, the magnetic pole drifted slowly over northern Canada, moving at a pace of a few miles per year in a rough oval pattern, predictable enough that navigators could account for it. Navigation charts were updated every 5 years, and the corrections were small. The pole's behavior was, by geological standards, placid. Then, in the late 1990s, something changed. The pole began accelerating. By the early 2000s, it was moving at roughly 22 miles per year. By 2020, it had crossed into the high Arctic. It is now aimed directly at Siberia, and the latest measurements put its speed at over 22 miles per year and still climbing. The acceleration was fast enough to cause a genuine operational problem. The World Magnetic Model, which is the international standard used by every navigation system on Earth, is updated on a 5-year schedule. It is the underlying model that tells your phone's compass which direction is north, tells aircraft autopilots how to correct their headings, and tells military guidance systems how to orient themselves. In 2019, the National Oceanic and Atmospheric Administration issued an emergency off-schedule update to the model. The pole had moved so far from its predicted position that the official maps had become meaningfully wrong before the scheduled revision date. That had never happened before. Meanwhile, the South Magnetic Pole is drifting at around 5.5 miles per year, less than a quarter of the North Pole's current speed. The planet's magnetic axis is twisting. The northern and southern poles are moving asymmetrically in different directions at different speeds, which means the geometry of the entire field is changing in ways that a simple shift of both poles together would not produce. The magnetic field is reorganizing, and the reorganization has no symmetry. The poles are accelerating. The South Atlantic anomaly is growing. The overall field is weakening. Taken individually, each of these observations has an explanation rooted in the dynamics of the outer core. Taken together, they describe a system in transition, and the asymmetry between the two poles is particularly telling. Deep in the outer core, opposite hemispheres are generating magnetic flux differently. The patch of reversed flux beneath the southern hemisphere that contributes to the South Atlantic anomaly is altering the way the southern part of the dynamo behaves. The northern part of the outer core is responding differently, producing a pole that accelerates rather than drifts. The two hemispheres of the same system are out of balance in a way that produces this asymmetric behavior at the surface. Understanding why is at the frontier of current geomagnetic research, and tucked inside the scientific literature on Earth's magnetic field is one more phenomenon that gets almost no public attention, one that gives the transition a different kind of texture. The pole is sprinting. The anomaly is expanding. The overall field has lost roughly 10% of its strength over 2 centuries. None of that prepared researchers for what the field occasionally does between those slow trends. Because every few years, without warning, without prediction, and without a clear pattern, it lurches. Every few years, Earth's magnetic field experiences what researchers call a jerk. The name is used in its precise physical sense. A sudden, sharp change in the rate at which the field is changing. If the field were a car, a jerk would be an abrupt shift in acceleration, a discontinuity in the behavior rather than the behavior itself. It's detectable as a V-shaped kink in the records at magnetic observatories, a moment when the smooth trend in one direction snaps to a new trajectory. Confirmed jerks, identified by combing historical observatory records going back to 1901, occurred in 1925, 1969, 1978, 1991, 1999, 2003, 2007, 2011, 2014, 2017, and 2020. They range from regional events affecting only part of the field to global events that snap the behavior of the field across the entire planet simultaneously. Their intervals are irregular, ranging from roughly 3 years to 12 years. There is no discernible periodicity. The mechanism was identified in a 2019 study in Nature Geoscience. Deep inside the outer core, buoyancy-driven releases of energy launch pressure waves called Alfvén waves through the liquid iron. These waves travel outward from the deep core over the course of roughly 25 years. When they reach the boundary between the outer core and the solid mantle above it, they erupt, causing the field to suddenly shift direction. The waves travel for decades through liquid metal before arriving at the surface and snapping the field into a new trajectory. The horror in this, and there is a genuine intellectual horror here, is that the waves are unforeseeable. The same mathematical chaos that makes weather prediction unreliable beyond roughly 2 weeks makes the geomagnetic field fundamentally unpredictable beyond a few decades. Julien Aubert, a researcher at the Paris Institute of Earth Physics who studies the geodynamo, has stated plainly that the field cannot be predicted more than a few tens of years in advance. The jerks, in his description, are the extremes of geomagnetic behavior, the crises, like tornadoes in a weather system. They arrive without warning. There is no physical model that can forecast when the next one will happen. We know they happen. We cannot predict them. We know one is coming. We don't know when. What a jerk actually means for the systems civilization depends on is worth making concrete. Each time one occurs, the magnetic field shifts its direction and rate of change abruptly enough to render existing navigation models less accurate. The world magnetic model is updated on a 5-year schedule, and the updates assume the field is drifting smoothly in a predictable direction. A jerk violates that assumption. The 2014 and 2017 jerks, arriving close together, contributed to the degradation in model accuracy that triggered the emergency update in 2019. The frequency of the jerks is itself a data point. The 3 to 12-year interval between events is wide enough that any given jerk seems isolated. But 11 confirmed events since 1901 reveal a pattern of regularity beneath the irregularity. The outer core has been launching Alfvén waves at roughly that cadence throughout the entire modern era. The ones that will produce jerks in the next 2 decades are already traveling upward through the liquid iron right now, and there is no instrument that can see them coming. Then, in September of 2025, satellites detected something unexpected over the Atlantic. A gravitational signal, planet-sized in scale, coinciding with a geomagnetic jerk. The instruments saw it clearly. The explanation hasn't been fully published yet. Satellites detected the signal in September of 2025, and the scale of what they measured was immediately difficult to make sense of. 2 separate satellite systems contributed to the finding. The National Aeronautics and Space Administration and the German Aerospace Center operate a pair of gravity-sensing spacecraft called the Gravity Recovery and Climate Experiment Follow-On. which fly in tandem about 137 miles apart and measure the gravitational pull of whatever lies beneath them by tracking the distance between the two spacecraft with extraordinary precision. When one satellite passes over a region of higher than expected mass, it accelerates slightly, changing the gap. That change, measured in microns, translates into a gravity map of whatever lies below. The system was designed to track changes in ice sheet mass, groundwater reserves, and ocean circulation. In September of 2025, it detected something for which ice and water were insufficient explanations. A gravity anomaly spanning roughly 7,000 kilometers over the Atlantic coincided, within a short window, with a confirmed geomagnetic jerk event. 7,000 kilometers is roughly the distance from London to Tokyo. A gravitational disturbance of that scale implies mass redistribution at depth, movement in the mantle or at the core mantle boundary large enough to create a measurable gravitational signature from orbit. The coincidence of a magnetic jerk and a gravity anomaly is significant because jerks originate at the core mantle boundary. The Alphen wave packets described in the previous chapter, which travel upward through the liquid outer core for roughly 25 years before erupting at that boundary and snapping the field, carry energy. If that eruption is energetic enough, and if it drives mass redistribution in the deep mantle, it could in principle produce a gravitational signature detectable from orbit. Whether that is precisely what happened is, as of early 2026, still being investigated. The observation is confirmed. The mechanism connecting the gravity anomaly to the jerk has not yet been fully published. What makes this detail significant for the larger argument of this video is the fact that these two things, a planet-sized gravitational fingerprint and an abrupt shift in the magnetic field, were happening simultaneously. The instruments registered both. The explanation is still being assembled. Every chapter so far has described something that required decades of data and highly specialized instruments to detect. The doublet earthquake method needed Cold War nuclear test recordings from a vanished superpower. The acceleration of Earth's rotation required 50 years of atomic timekeeping. The South Atlantic anomaly's precise expansion rate required 11 years of data from 4 satellites in polar orbit. Each discovery needed a specific tool that only recently became precise enough to see the signal. And now, with each of those tools operating simultaneously, they are detecting signals that interact with each other in ways the original designers of each instrument could never have anticipated. A gravity satellite built to track melting ice found a deep mantle signature coinciding with a magnetic event detected by field strength sensors. A system designed to watch water redistribution picked up the echo of something moving 3,000 miles underground. The field is shifting. So is everything else. And the deepest irony is that the next piece of this story involves the one source of planetary perturbation that required no specialized instruments at all. It required only a well pump. Beneath the American Midwest, northwestern India, and the arid plains of the Middle East, aquifers hold water that accumulated over tens of thousands of years. They are among the planet's most important resources, ancient reserves drawn from with increasing intensity since the middle of the 20th century. The extraction of that water, it turns out, did something to the planet itself. In 2023, a research team at Seoul National University published a study in Geophysical Research Letters demonstrating the following. Between 1993 and 2010, the redistribution of groundwater pumped from aquifers around the world shifted Earth's rotational axis by approximately 80 centimeters eastward. That is roughly 2.5 feet. The methodology behind the finding is worth understanding. The team built a climate model of polar drift, the natural wandering of Earth's rotational axis resulting from changes in mass distribution at the surface. When they ran the model using all the standard inputs, It matched historical observations of polar drift well, but a consistent gap remained between model and reality. A portion of the observed drift, especially its direction and acceleration, was unexplained. When the researchers added groundwater extraction to the model, quantifying the mass of water pumped from underground reserves and redistributed into the world's oceans, the gap disappeared. Over 2 trillion tons of water were pumped from the ground during that period and released into ocean basins. Place that volume of water on the equatorial ocean, farther from Earth's rotational axis than where it sat underground in mid-latitude aquifers. And the rotational axis must compensate. Physics requires it. To be clear about what this means physically, the rotational axis of Earth, the invisible line around which the entire planet spins, moved. The geographic North Pole traces a small irregular circle year to year due to natural wobbles in Earth's rotation. That circle itself drifted. In 1995, the direction of polar drift changed sharply, turning from a generally southward trajectory to an eastward one. The speed of polar drift increased 17-fold between the period from 1981 to 1995 and the period from 1995 to 2020. The groundwater extraction model accounts for this shift and acceleration. Glacial ice melt contributed as well, and its contribution has been recognized for longer. What the 2023 study added was the groundwater component, which filled the remaining gap and pointed to human water use as a geological agent. This is worth sitting with. The pumping of water from underground reserves, an activity done for irrigation and municipal supply by farmers and cities making ordinary daily decisions, physically relocated the rotational axis of a planet. No individual well produced this effect. The aggregate of countless ordinary decisions made over 17 years across the American Midwest and Northwestern India and the deserts of the Middle East moved Earth. Humanity left a measurable geological footprint, written in the direction a planet points. And we were far from the only force doing it, because the ice sheets have been doing the same thing on a far larger scale over a far longer timeline, and the projections for what they will do before this century ends are larger still. Calculating where Earth's rotational axis will be in 75 years requires knowing the future of the ice sheets. And knowing the future of the ice sheets requires knowing the future of emissions. And knowing the future of emissions requires assumptions about human behavior across every economy on Earth. The uncertainty stacks, and yet, even accounting for that stacked uncertainty, the projections for polar shift by 2100 are large enough to matter for the infrastructure calibrated against the current pole position. A federally funded analysis published in 2024 used 120 years of observational data and machine learning to separate the contributions to polar motion. The result: 90% of the recurring fluctuations in Earth's rotational axis between 1900 and 2018 can be explained by surface water changes, meaning ice sheets, glaciers, groundwater, and sea level. The remaining 10% comes from Earth's interior dynamics, including what the authors describe as a wobble contributed by the tilt of the inner core relative to the planet's bulk. There it is again. The same inner core whose deceleration began around 2010 is contributing to the drift of the planet's spin axis. The deep interior and the surface are co-authoring the same shift from opposite ends of the planet. The projected axis shifts under continued ice melt range between 12 and 27 meters by 2100. 12 meters is roughly the length of a school bus. 27 meters is about the width of a modest apartment building. These are distances, not geological abstractions. The navigational infrastructure that civilization has built on top of this planet was calibrated to where the axis was when the infrastructure was built. Satellite navigation systems, to function with the precision that modern navigation, agriculture, and autonomous systems require, are linked to a precise reference frame for Earth's orientation in space. That reference frame is based on the current pole position. As the pole drifts, the reference frame drifts with it. Every satellite in every navigation constellation, every ground station that tracks them, every application that depends on positional accuracy requires continuous recalibration to account for the shift. The error is small in any given year, but it accumulates. The World Magnetic Model, which already required an emergency update in 2019 to account for the magnetic pole's sprint, is a separate calibration challenge. The rotational pole shift and the magnetic pole shift are independent processes driven by different physical mechanisms, but both affect navigation systems, and both are accelerating simultaneously. The practical consequence is that the planet is slowly pointing in a different direction, and every system that depends on knowing precisely which direction that is will require more frequent and more substantial updates to remain accurate. The systems were designed for a planet that stayed roughly where it was. The planet is moving. Every thread from the first 14 chapters connects to something below the surface or above it or inside it. The axis is drifting. The magnetic poles are sprinting. The rotation is accelerating. All of it traces back to the same melting ice that is simultaneously doing something to the ocean, something that may be the most consequential single item on this entire list. Picture a lava lamp. Dense fluid at the bottom heats up, becomes less dense, rises. At the top, it cools, becomes dense again, and sinks back down. The cycle continues indefinitely, driven by a heat source at the bottom and the difference in density between warm fluid and cold fluid. This mechanism, essentially unchanged from a living room novelty, is the operating principle of the most important ocean circulation system on Earth. The Atlantic meridional overturning circulation moves an enormous volume of water in a pattern that has been running for millions of years. Warm, salty water flows northward from the tropics through what most people call the Gulf Stream, carrying heat from the equatorial Atlantic toward the far north. As this water moves through the North Atlantic, it releases its heat to the atmosphere above it. That release is what makes northern Europe habitable. London sits at roughly the same latitude as the southern coast of Hudson Bay in Canada. It experiences winters measured in degrees above freezing, while Hudson Bay is locked in sea ice. The difference is almost entirely attributable to the heat carried north by this circulation. Without it, the average temperature of northwestern Europe drops by roughly 10 to 15 degrees, and the agricultural and energy infrastructure built for current conditions becomes incompatible with the climate that would replace them. The heat-released water, now cooler and still very salty, becomes dense enough to sink. It descends several thousand feet, flowing southward along the ocean floor in a deep current that eventually joins the global ocean conveyor. The journey from the North Atlantic sinking zone to the ocean's far reaches takes over 1,000 years. The water that sinks today will resurface somewhere in the Southern Ocean or Pacific in a millennium. The key variable in this system is salinity. Salty water is denser than fresh water. The sinking that drives the circulation depends on the water being dense enough to descend. Remove the salt, dilute the water with something fresher, and the water no longer sinks. If it doesn't sink, the conveyor belt stalls. The circulation weakens or stops. This is why the word that matters most in any discussion of the Atlantic meridional overturning circulation is salinity. The ocean's saltiness is the engine's fuel, and for the past several decades, the engine has been receiving an increasing dose of something that acts like a wrench in the gears. Fresh water, pouring in from the north in quantities that have no equivalent in the modern era. The circulation has weakened roughly 15% since the middle of the 20th century. This is a measured value, derived from proxy records and modern instrumentation. A 15% reduction in the volume of water being transported northward means 15% less heat reaching the latitudes that depend on it. 15% less cold water sinking at the poles. 15% less momentum. driving the entire global deep ocean circulation system. The system is elegant. It has survived ice ages, warm periods, and the full range of Earth's recent climate variability. Its elegance comes from its simplicity. Heat, water, make it salty, let it cool, let it sink, let it rise elsewhere. The same simplicity that makes it robust is what makes it vulnerable. There is one thing it cannot compensate for, and that one thing is exactly what is being poured into the North Atlantic right now, at an accelerating rate, with no sign of slowing. The system is being poisoned by fresh water, and the source of that fresh water is not going to stop. South of Greenland, the ocean's surface looks wrong. Every piece of temperature data from the past decade shows the same feature: a persistent patch of anomalously cold water sitting in the middle of an ocean that has otherwise been breaking heat records in every direction. In 2024, the global ocean reached its highest average surface temperature since records began. The waters around the British Isles were extraordinarily warm. The tropical Atlantic was warm. The waters south of Iceland were warm. And south of Greenland, surrounded on all sides by this record warmth, there was a cold blob. That cold blob is the most visible evidence that the Atlantic meridional overturning circulation is weakening. It exists because the circulation is failing to distribute heat through the region the way it used to. When the overturning is vigorous, warm water reaches that part of the ocean and heats it. When the overturning slows, the warm water stops arriving, and the region cools relative to its surroundings. The blob is a diagnostic fingerprint. The pattern appears in virtually every climate model simulation of a weakening circulation, and it is now present in the real ocean. The mechanism producing it connects directly to the previous chapter's description of the circulation's vulnerability. Greenland is melting at an accelerating rate. Fresh water is less dense than the salty North Atlantic water it mixes with. It floats, it spreads, and it forms a surface layer that resists the cooling and sinking process that drives the circulation. Warm water from the tropics that should sink in this region cannot, because the surface layer has been freshened. The heat stays near the surface, where it warms the atmosphere rather than descending to drive the deep circulation. The cold blob grows and persists because the heat redistribution process has slowed. The region south of Greenland is cold because warm water from the south is arriving less efficiently and sinking even less. The 15% weakening, measured since the mid-20th century, represents a level of Atlantic overturning strength that has no parallel in the last millennium. Proxy records, built from sediment cores and marine fossils that preserve information about past ocean temperatures and productivity, have allowed researchers to reconstruct the circulation's history going back hundreds of years. The current level of weakening is the lowest in that entire record. The cold blob has been persistent across multiple years. Cold blobs can appear for other reasons, and early skeptics suggested the feature might be transient. The accumulation of data from 2020 through 2025 showed it was stable and exactly where every weakening model predicted it would form. And in 2025, satellites watching the ocean's surface detected something that moved the argument from correlation to something considerably more direct. The pattern that researchers had seen only in computer simulations, the one that appears in models before everything changes, was showing up in the actual ocean. When scientists described what they were seeing, they reached for a specific word that carries specific weight in the vocabulary of climate science. That word is precursor. Ocean surface measurements can capture things that no stationary buoy could ever see: the position, speed, and trajectory of currents spanning hundreds of miles and carrying enough water to dwarf all of the world's rivers combined. Since 1993, a constellation of satellites carrying radar altimeters has been continuously measuring the height of the ocean surface to within a few centimeters. The Gulf Stream creates a ridge of slightly higher water on its eastern edge, a consequence of Earth's rotation pushing the current against the pressure gradient it generates. Track that ridge over time and you track the stream itself. The data collected between 1993 and 2024 shows something that had never appeared before in the observational record. The Gulf Stream near Cape Hatteras, the stretch of the American East Coast where the current typically turns northeast and leaves the continental shelf, has shifted its path. The shift is northward. The stream's main axis has moved, and the movement is statistically robust across 3 decades of satellite measurements. A study published in 2025 in a leading Earth science journal established the significance of this observation by comparing it with climate model output. In simulations that model a full Atlantic overturning collapse, a pattern of abrupt Gulf Stream path changes appears consistently in the years leading up to the collapse event. The simulated timing of this precursor signal places it, on average, a few decades before the collapse itself. The researchers described the Gulf Stream's path change as a warning sign that, in their models, reliably preceded the transition to a weakened or collapsed circulation state. That precursor signal is now present in the real observational data. In medicine, elevated blood pressure and abnormal cardiac rhythms are precursors to events that have not yet occurred. Finding them changes the probability assessment. It changes what a responsible clinician does next, and it changes the framing of the conversation. The framing shift that the Gulf Stream observation demands is this: we are no longer discussing whether the Atlantic circulation is weakening in the abstract. We are observing a specific behavioral change in a major component of that circulation that, in every simulation studied, appears before the system crosses a threshold from which it does not return. The observation does not tell us how long before. It tells us which side of that behavioral change we are currently on. The precursor has appeared in the data. The question is what comes next, and the answer depends on the models and on what the models say about probability. But the timeline attached to those models, when you look at it directly, is precise enough to feel personal. The projections do not describe something happening in a distant geological era. They describe a window that falls within the lifetimes of people who are already alive. The Atlantic overturning has a measurable precursor in the real ocean and a best estimate collapse window sitting inside the remaining decades of people alive today. The probability attached to that window, when researchers calculate it using physical models calibrated against observations, is one of the more unsettling specific numbers in contemporary science. Models cannot tell you exactly when something happens. That is an intrinsic feature of complex systems, where small uncertainties in initial conditions and feedbacks compound into large uncertainties in outcome. What models can do is calculate probabilities across ranges of outcomes and identify where the weight of the evidence points. For the Atlantic meridional overturning circulation, a physics-based model published by researchers at Utrecht University in 2024 did exactly that, with results that are difficult to sit with comfortably. The mean estimate for circulation collapse, using a model calibrated against the freshwater transport signal at the most sensitive indicator location in the South Atlantic, comes out around 2050. The range of the 95% confidence interval spans 2037 to 2064. The probability of collapse before 2050 is 59%. There is a tendency to take comfort in wide error bars as evidence of uncertainty that makes an outcome unlikely. That tendency is precisely backward. The fact that even a 95% confidence interval spans only a 27-year window means we are committed to a trajectory toward a threshold we cannot precisely locate, within a window that falls inside the remaining lifespan of people alive today. What a collapse looks like. Based on the paleoclimate record of the last time it happened, roughly 12,000 years ago, during the period called the Younger Dryas, gives the probability of physical shape. Temperatures across Europe and North America fell 10 to 15 degrees within a decade. Monsoon circulation in South Asia, the Sahel, and South America was disrupted, with multi-year drought conditions affecting some of the most agriculturally productive regions on Earth. Sea levels along the United States East Coast rose significantly as the circulation's natural depression of coastal sea levels was removed. The Amazon entered prolonged drought. A decade is a very fast timescale for a temperature shift of that magnitude. The agricultural systems, energy infrastructure, and coastal engineering of northern Europe, the east coast of the United States, and the monsoon-dependent populations of West Africa and South Asia were built for the climate the overturning circulation maintains. None of them were designed for the climate that would replace it. Once the collapse crosses a tipping threshold, the feedbacks become self-reinforcing and the reversal of the process on human timescales becomes effectively impossible. Less salt transported northward means less sinking, which means less salt transport, which means less sinking. The weakening drives itself. There is no natural mechanism that restores a collapsed overturning circulation on anything shorter than a geological timescale. The scientific community is appropriately cautious about exact timing. There is legitimate debate about the models and the statistical methods used to estimate collapse probability. The error bars are real, but the direction of the evidence across multiple independent research groups using different methods and different data sets points the same way. The ocean is the largest heat engine on Earth. Its pump is faltering. And while researchers were focusing on the Atlantic, something happened somewhere else that crystallized everything about this story in a single quiet event that almost nobody, anywhere, noticed at all. November 11th, 2018, 9:30 in the morning. Coordinated Universal Time. A signal begins radiating outward from the ocean floor roughly 15 miles off the eastern coast of a small French island in the Indian Ocean called Mayotte, a volcanic archipelago sitting between Madagascar and the northern tip of Mozambique. The signal travels across Africa. Sensors in Zambia register it. Sensors in Kenya and Ethiopia register it. It crosses the Atlantic and is detected in Chile. It reaches New Zealand. It arrives in Canada and Hawaii, nearly 11,000 miles from its origin. It has been traveling for 20 minutes. No one felt it. The signal was below the threshold of human perception, too low in frequency to register as sound or vibration. It was entirely invisible to the automatic detection algorithms that global seismic networks use to identify earthquake events because it looked nothing like an earthquake. It was monochromatic, carrying essentially a single pure frequency, repeating every 17 seconds like a note played continuously on an instrument of planetary scale. A leading seismologist at Columbia University said he had never seen anything quite like it. The automatic systems didn't flag it. The professional networks didn't catch it. It was first spotted by a single person, an amateur earthquake enthusiast monitoring the United States Geological Survey's real-time seismic display from home, who noticed strange, regular zigzag patterns on the live feed and posted about them online. That post started an international scientific scramble. The explanation took over a year to establish and was published in the journal Nature Geoscience in 2020. A new submarine volcano was being born on the seafloor off Mayotte, a structure 3 miles long and nearly a mile tall, growing in the deep ocean as magma poured upward from below. As a massive deep magma reservoir drained, the rock above it began to destabilize, and the reservoir started resonating, dilating, and contracting on a precise 17-second cycle, sending that ghost signal around the planet for months. The November 11th event was the loudest moment of a pulse that had been running well before any human detected it. Mayotte subsequently sank 8 inches and shifted several inches eastward as the seafloor adjusted to the drainage. 260,000 residents live on the island. Ongoing monitoring of the volcanic structure's activity has continued ever since. The reason this event belongs in this video is precise. The planet was giving birth. It had been pulsing for months, sending a planetary scale signal across 11,000 miles of ocean and rock, and almost nothing in the global scientific infrastructure had the capacity to detect it as it was happening. It took one person with curiosity and an internet connection to initiate the response. The monitoring gap was closed only in retrospect, after the source was identified. Every chapter in this video has described a system that was already behaving differently before the instruments caught up. The inner core slowed for over a decade before the confirmation. The magnetic pole was sprinting before the emergency map update. Mayotte was pulsing for months before a tweet. Earth communicates in frequencies we are barely equipped to hear. Now consider what has been happening in the sky above us, in the layer that stands between everything alive on this planet and the radiation of open space. Ask most people what they know about the ozone layer, and they will tell you the same story. Chlorofluorocarbon emissions from aerosol sprays and refrigerants were tearing a hole in the protective layer above Antarctica. Scientists identified it. Governments acted. The Montreal Protocol of 1987 banned the offending chemicals. Emissions fell by over 99%. The Antarctic ozone hole began shrinking. The layer was healing. The story has been taught in schools for 3 decades as a model of what international environmental cooperation can achieve. The good news is genuine. Chlorofluorocarbon emissions have fallen dramatically. The Antarctic ozone hole is measurably smaller than it was in the 1990s. The Arctic ozone layer is projected to recover to its 1980s level by 2045. Antarctic recovery is projected for 2066. This is real progress that took real effort. 30 years of coordinated international work purchased a meaningful and growing recovery. The layer is still about 2% below pre-industrial levels. There are now 2 new problems. They are entirely different from chlorofluorocarbons in their origin and mechanism. Neither is covered by the Montreal Protocol. Neither has any international regulatory framework addressing the stratospheric chemistry it produces. And both are accelerating simultaneously, arriving precisely as the recovery from chlorofluorocarbons was finally gaining traction. The first comes from below the ozone layer, climbing through it on a growing trajectory. The second comes from above, descending through it from space. They arrived as new threats in roughly the same era. They operate through different chemical pathways, and they arrive at the same outcome: stratospheric ozone molecules destroyed. The layer that the Montreal Protocol spent 3 decades beginning to heal is now being pressured from 2 new directions that the treaty was never designed to address and has no mechanism to constrain. There is no international body with authority over either source. No emission limits have been set, no phase-down schedules have been agreed. No monitoring requirements have been established. The shape of the problem is different from chlorofluorocarbons. Those emissions were steady and accumulating. They built up in the stratosphere over years and decades, and once the sources were removed, the chemistry that destroyed them slowly cleared. The 2 new threats operate differently. One is episodic and intensifying. The other is growing steadily with no natural ceiling in sight. Together, they produce a pattern where the recovery that was supposed to continue into mid-century begins to slow, stall, or in certain regions reverse. The honest position is that the ozone layer is recovering. The equally honest position is that the conditions under which that recovery was projected were calculated without these 2 new sources included. Including them changes the projections. 2 problems. One comes from below, climbing through the stratosphere. The other comes from above, descending through it. Both are accelerating simultaneously. Let's look at the one that comes from below first, because the scale of its growth in the past 6 years is one of the harder numbers in this entire story to absorb. Orbital launches have become so routine that most people stopped paying attention years ago. A rocket lights up, climbs through the atmosphere, delivers its payload, and the coverage lasts until the next one. The cadence has become background noise, and that normalization has obscured something important. The actual numbers involved in the growth of launch activity over the past 6 years are extraordinary, and the chemical consequences of those launches are entirely unregulated. In 2019, there were 97 orbital rocket launches worldwide. By 2024, That number had risen to 258, a near tripling in 5 years. Projections based on announced programs from SpaceX, Amazon, the European Space Agency, Chinese state launch providers, and a growing catalogue of commercial operators suggest the number could reach 2,000 or more annually by 2030. The driving force is satellite mega-constellations, networks of tens of thousands of small satellites requiring continuous replenishment as individual units reach the end of their operational lives. Each launch injects material directly into the stratosphere, the layer of the atmosphere between roughly 10 and 50 kilometers above the surface that contains the ozone layer. The substances deposited vary by rocket design and propellant type, but the common constituents include black carbon particles, aluminum oxide particles released from solid fuel component burnup, reactive chlorine compounds from solid propellant combustion, nitrogen oxides, and water vapor. In the troposphere, the lower atmosphere where weather occurs, these materials would disperse and react relatively quickly. In the stratosphere, the chemistry works differently. There is no rain to wash particles out. There are no weather systems to mix and dilute. A particle deposited in the stratosphere can remain there for months or years, up to 100 times longer than equivalent particles at ground level. Aluminum oxide particles are particularly significant. They provide surfaces on which ozone-destroying chemical reactions can occur, analogous to the role that polar stratospheric cloud particles play in producing the Antarctic ozone hole. More launches mean more aluminum oxide particles. More aluminum oxide particles mean more reactive surfaces available for ozone destruction. A modeling study published in 2024 by researchers at the Swiss Federal Institute of Technology in Zurich and confirmed by a subsequent University of Canterbury analysis in 2025 quantified the projected impact under different growth scenarios. Under a moderate scenario of 884 launches per year, global ozone thins by approximately 0.17% by 2030. Under the high-growth scenario of roughly 2,000 launches per year, the global thinning reaches approximately 0.29%, with regional losses over Antarctica reaching up to 4% seasonally. 4% over Antarctica. The ozone layer there has been recovering for 3 decades, gaining roughly 1 to 3% of lost thickness per decade. 4% of seasonal loss in a single region would reverse a decade of Antarctic ozone recovery in 1 year. There is no international treaty governing rocket emissions in the stratosphere. The Montreal Protocol, which governs stratospheric ozone protection, covers chlorofluorocarbons and related compounds from industrial and consumer products. It does not cover rocket exhaust. No regulatory body has been established. No emission limits have been proposed. No phase-down schedule exists. The rockets come from below. The other threat descends from smoke. Australia experienced something in the summer of 2019 and 2020 that reshaped how atmospheric scientists think about ozone layer risk. The fires that became known as Black Summer burned across an area of nearly 47 million acres, making them the most extensive and intense wildfire events in the country's recorded history. The fires generated smoke plumes that rose high enough and with enough energy to punch through the troposphere and enter the stratosphere directly. Once in the stratosphere, the smoke particles did something researchers had not fully anticipated at that scale. Wildfire smoke contains aerosol particles coated with reactive nitrogen and organic compounds. In the cold, dry conditions of the stratosphere, these particles trigger ozone-destroying chemical reactions. The specific pathway involves aerosol surfaces catalyzing the conversion of stable nitrogen compounds into reactive forms that then attack ozone molecules. The chemistry is different from the chlorofluorocarbon pathway, but the outcome is the same. A study published in 2022 analyzing stratospheric chemical measurements taken before, during, and after the Australian fires found that the smoke had destroyed roughly 1% of the ozone layer across the entire southern hemisphere within months of the fire season. 1% is a large number in this context. The layer that took 30 years to begin recovering had its recovery partially reversed by a single fire season. Climate change is making large wildfire events more frequent and more intense. The conditions that produced Black Summer, extreme heat, extended drought, and low humidity over a continental landmass are becoming more common as the global average temperature rises. Australia's fire seasons are getting worse. So are those in the western United States, the Mediterranean basin, Siberia, and the boreal forests of Canada. Each major fire season is a one-time injection of ozone-depleting chemistry into the layer. The Montreal Protocol removed the steady, accumulating source of chlorofluorocarbons. It was designed to address persistent industrial emissions with no mechanism for episodic high-intensity injections from fires. The two threats introduced in the previous two chapters have a structural relationship worth making explicit. Rocket exhaust is a growing, steady, compounding source of stratospheric contamination with no regulatory ceiling. Wildfire smoke is an episodic source that arrives in large doses and is becoming more frequent and more intense with each decade. The ozone layer faces a slow, steady bleed from one direction and periodic large wounds from another, arriving at a moment when the slow recovery from chlorofluorocarbons is still incomplete. The recovery was supposed to continue on a smooth upward trajectory to full restoration by mid-century. The trajectory is being interrupted. The layer is being healed slowly from one direction and hit from two new angles simultaneously. The shield is under pressure from fire below and rockets above. But the most disorienting part of the atmospheric story is not what is attacking the ozone layer from outside. The deeper irony involves something that happened over decades of ordinary industrial activity, something that altered the atmosphere in a way that nobody planned for and nobody fully understood until it was already well underway. For 40 years, without intending to, without knowing it, and without any coordinated decision to do so, human industrial activity had been running a planetary cooling experiment. The experiment worked, and when it ended, the accumulated warming that had been quietly waiting behind it finally arrived at the surface. The scale of what was masked, and the speed at which the masking ended, is one of the stranger chapters in the story of how this planet actually works. From roughly 1950 to 1990, something was happening to the amount of light reaching Earth's surface that nobody planned for, nobody coordinated, and very few people noticed in real time. The amount of solar energy arriving at the ground dropped by 4 to 6% globally over those 4 decades. Scientists would later call this phenomenon global dimming. The mechanism was industrial air pollution. Factories burning coal across the northern hemisphere released vast quantities of sulfate, aerosol particles, and black carbon into the atmosphere, where they scattered and absorbed incoming solar radiation before it could warm the surface beneath them. The effect was enormous by the standards of Earth's energy budget. A 4 to 6% reduction in incoming solar energy over 40 years is large enough to meaningfully suppress surface temperatures globally. The aerosols were acting as an inadvertent sunshade, a parasol made of industrial pollution that happened to intercept the same energy that greenhouse gases were trapping below. The two effects partially cancelled each other out. This is why, during a period when greenhouse gas concentrations were rising substantially, the global average surface temperature did not rise as fast as the greenhouse forcing alone would have predicted. The planetary cooling experiment ran because countries were burning coal and oil at industrial scale. Nobody chose to run it. Nobody announced it. It simply happened as a byproduct of economies trying to generate energy and goods. For 40 years, it masked the full power of the warming accumulating beneath it. Then the experiment began to end. Starting in the 1980s in Europe and North America, and gradually spreading through subsequent decades, air quality regulations began reducing the amount of aerosol pollution entering the atmosphere. The air got cleaner. The parasol became thinner. More solar energy reached the surface. Scientists named this transition global brightening, and as the dimming reversed, the greenhouse warming that had been building behind the aerosol shield became visible at the surface. The rapid temperature rises of the 1990s and the accelerating warmth of the early 2000s are partly explained by this unmasking. The greenhouse gases had been accumulating throughout the dimming period, and the warming they were capable of producing had been suppressed. When the suppression weakened, the suppressed warming arrived. China's trajectory illustrates the timeline in concentrated form. Chinese solar radiation data shows substantial dimming from the 1960s through the 1990s as industrialization surged, followed by signs of brightening from roughly 2007 onward as the country implemented clean air policies. India, meanwhile, continues showing declining sunlight through the current period, still deep in its dimming phase, its industrial pollution still providing inadvertent cooling even as its greenhouse emissions contribute to warming. Every major economy is at a different position on the same trajectory, unmasking the warming in staggered waves over different decades. The experiment worked for as long as it ran. The cooling was real. The suppression was real. And now the deeper question concerns what happens when the remaining aerosol pollution clears, because the backlog of suppressed warming does not disappear when the dimming ends. It waits, and the scenario where it arrives all at once has a name, and that name describes a trap with two exits, and both exits lead somewhere worse than addressing this earlier would have. Every serious climate model that tries to forecast the consequences of rapid decarbonization encounters the same uncomfortable feature buried in the relationship between aerosols and greenhouse gases. The feature does not resolve cleanly in any direction. Scientists call it termination shock, and it describes a scenario where doing the necessary thing quickly could temporarily make things worse before they get better. The structure of the trap is as follows. Greenhouse gases are long-lived. Carbon dioxide, once emitted, remains in the atmosphere for centuries. Its warming effect does not increase immediately with new emissions and does not diminish immediately when emissions stop. The accumulated stock of greenhouse gases in the atmosphere right now will continue warming the planet for decades even if every emission source on Earth were shut down today. Aerosol pollution, by contrast, is short-lived. Sulfate particles from coal combustion, the same particles responsible for the global dimming described in the previous chapter, fall out of the atmosphere within weeks to months. They provide cooling only as long as they are continuously produced. Stop producing them, and the cooling vanishes almost immediately. If the world were to decarbonize rapidly, eliminating fossil fuel combustion over the span of a decade or two, the aerosol pollution still present in the atmosphere would clear within months of the fuels stopping. The greenhouse gases accumulated over a century and a half would remain. The result would be a brief but potentially significant window where the insulating effect was unchanged, while the cooling effect from aerosols disappeared. Some estimates place the potential unmasked warming at between 0.5 degree and 1 degree above current levels in the short term, above and beyond the warming already projected from existing greenhouse gas concentrations. The trap has two exits, and both lead to worse outcomes than addressing the underlying problem earlier would have. Slow decarbonization keeps aerosols present longer, which means it also keeps adding greenhouse gases, deepening the long-term warming. Rapid decarbonization eliminates the aerosols quickly and exposes the backlog. The models cannot clearly identify a safe corridor between them, a pace of transition fast enough to prevent long-term harm without triggering short-term unmasking. China's real-time transition illustrates the practical dimension. As the country's clean air policies took effect from around 2007, solar radiation at the surface increased, exactly as the dimming research predicted it would. The warming that dimming had been suppressing is now being progressively exposed. The faster the remaining aerosol sources in developing economies clean up, the more quickly the unmasking completes itself. And the more greenhouse gases already in the atmosphere when that happens, the larger the exposed backlog. The honest position from atmospheric scientists is that the termination shock risk is real. It has not been fully quantified, and no current climate policy framework explicitly accounts for it. The transition away from fossil fuels is necessary. The transition creates a short-term risk that is not being discussed at the scale the problem deserves. The atmosphere above us is layered with interdependencies built over decades of industrial activity, and understanding them fully has taken longer than the activity itself. There is one more layer to introduce, one that connects the deep interior, the magnetic field, the boundary between atmosphere and space, and the surface in a single physical system. It pulses. It has always pulsed, and right now, multiple things are simultaneously changing the conditions that govern it. Since lightning began striking Earth's surface, the planet has been resonating. Every lightning bolt sends an electromagnetic pulse radiating outward. That pulse bounces between the surface and the ionosphere, the electrically charged layer at the top of the atmosphere roughly 60 to 1,000 kilometers above the ground, and the bouncing creates a standing wave. The geometry of the cavity between the ground and the ionosphere means that specific frequencies resonate more efficiently than others, accumulating energy rather than dispersing it. The strongest of these natural resonant frequencies works out to approximately 7.83 cycles per second. Scientists call this the Schumann resonance. Others have called it Earth's heartbeat. 100 lightning strikes happen every second across the globe. Each one contributes to the excitation of this electromagnetic cavity. The resonance has been present and measurable since the earliest days of radio science, and it has been continuously monitored at stations around the world for decades. It fluctuates naturally with the 11-year solar cycle, with solar flares, with seasonal changes in global thunderstorm activity. These variations are documented, understood, and unremarkable. The science of the Schumann resonance is, in most respects, well settled. What is less settled is what happens when multiple things change the conditions governing the cavity at the same time. The first factor is climate change itself. Rising global temperatures are increasing the frequency and intensity of thunderstorms, particularly in the tropics. More thunderstorms mean more lightning strikes. More lightning strikes mean stronger excitation of the cavity. The resonance has been gradually intensifying in a way that correlates with the increase in global thunderstorm activity. This is expected, understood, and currently modest in magnitude. The second factor is the weakening magnetic field. The field controls how deeply energetic charged particles from the solar wind can penetrate into the upper atmosphere. A stronger field deflects more of these particles before they reach the ionosphere. A weaker field allows more of them to penetrate to lower altitudes, depositing energy that heats and modifies the ionospheric boundary. The ionosphere forms the upper wall of the Schumann cavity. Change the ionosphere and you change the cavity. Change the cavity and you change the resonant frequency and the intensity of the signal. In February of 2026, monitoring stations recorded anomalous spikes in Schumann resonance readings, classified by the monitoring community as high and potentially disruptive. Researchers attributed these to intense solar activity interacting with a magnetic field already weaker than it was 50 years ago. The same solar event that would have produced a smaller ionospheric disturbance in 1970 produced a larger one in 2026, because the field protecting the boundary has been declining for 2 centuries and is still declining. There is a separate, smaller, and more contested area of research suggesting that biological systems that evolved alongside this resonance may respond to changes in its characteristic. Wheat plants showed measurable responses to magnetic fields in the resonance frequency band in a study published in 2023. A 2024 cardiac study noted potential biogeosynchronization effects in human rhythms. These findings are real peer-reviewed observations. They are also early, contested, and far from consensus. The honest statement about them is simply that life evolved alongside this electromagnetic pulse, and multiple things are now changing it simultaneously, and the implications have not been fully quantified. Earth has an electromagnetic heartbeat. The inner core is shape-shifting. The magnetic field is weakening. The climate is changing global lightning patterns. These are three separate processes, operating at different scales and speeds, all converging on the same cavity at the same moment in history. Now, step back. Look at all of it at once. Within each of the systems described in the previous chapters, there is a mechanism that does not merely allow the system to drift from its baseline. It accelerates that drift. Engineers call it positive feedback. The term in plain language describes a system where the output becomes an input in the same direction, so that movement away from equilibrium drives further movement away from equilibrium. These systems do not simply change. Once they begin changing past a certain point, they change faster. The Atlantic meridional overturning circulation's feedback is among the most clearly defined. The circulation runs on saltiness. Dense, salty water sinks in the North Atlantic, driving the conveyor. As the overturning weakens, it transports less warm, salty water northward. Less salt arrives in the North Atlantic. With less salt, the water becomes less dense. Less dense water sinks less efficiently. Less sinking means less overturning. Less overturning means less salt transport northward. The process feeds itself. Once the system crosses the threshold below which fresh water input from Greenland melt overwhelms the sinking, the collapse does not slow and reverse. It continues until the circulation has reorganized into a different state, and that reorganization takes geological time. The Arctic amplification feedback follows the same structure in a different medium. Ice and snow reflect solar radiation back to space. Open ocean and tundra absorb it. As warming melts sea ice, it exposes dark ocean surface beneath. That dark surface absorbs more energy than the ice it replaced, warming the water further, melting more ice, exposing more dark surface. The Arctic is currently warming 4 times faster than the global average, and the reduced ice cover is the primary explanation. The less ice there is, the faster the remaining ice melts. The groundwater feedback is less often discussed but follows the same logic. As aquifers deplete, the agricultural systems that depend on them require water from other sources. More water is sought from other underground reserves. Those reserves are also drawing down. As they deplete, surface agriculture becomes more precarious, which increases pressure on remaining subsurface reserves. The same axis shift that records the redistribution of extracted water will record the redistribution from the escalating extractions that follow. The geomagnetic feedback is the least well understood. As the magnetic field weakens, the ionosphere absorbs more charged particle energy from the solar wind. That energy heats the upper atmosphere. The heated upper atmosphere expands. The expanded atmosphere creates additional electromagnetic drag on the liquid outer core flowing through it. Additional drag could introduce perturbations to the core flow that affect the geodynamo generating the field. A weaker field could, in this way, contribute to conditions that keep it weaker. The mechanism is contested, the timescale is long, and the magnitude is uncertain. It is in the models. What makes this list significant is the simultaneity. Each feedback has been known in the scientific literature for decades. What is significant is that all of them are active at the same time, each reinforcing its own departure from baseline in systems that are physically coupled to each other. These systems do not drift separately, they accelerate away together, and the acceleration is not happening along disconnected trajectories. It is happening in systems that share inputs, share boundaries, and share the same moment in the measurement record. The correlation between them is not coincidence. The correlation is the discovery. Imagine being asked to diagnose a patient who presents with 11 separate abnormal test results. Each one, in isolation, has a plausible explanation. The elevated heart rate could be stress. The irregular blood pressure reading could be equipment error. The unusual blood chemistry could be a dietary artifact. You could write off each finding individually, note the uncertainty, and send the patient home. Or you could look at all 11 results together, in the same person, at the same moment, and recognize that the configuration of abnormalities is itself the finding. That second approach is what the science on Earth's current behavior demands. The inner core began slowing around 2010, and the confirmation arrived in 2024. Earth's rotation has been breaking speed records since roughly 2020. The South Atlantic anomaly expanded 8% in a single year, and the overall magnetic field has lost approximately 10% of its strength over 2 centuries. The magnetic North Pole began accelerating in the late 1990s, more than doubling its average drift speed, and is now heading toward Siberia at 36 kilometers per year. The direction of polar drift changed sharply in 1995, and the speed of that drift increased 17-fold over the following decades. The Atlantic meridional overturning circulation is at its weakest point in over a millennium. The cold blob south of Greenland has been persistent and growing across more than a decade of ocean temperature records. The Gulf Stream precursor signal is now present in observational data. The ozone layer is simultaneously recovering from chlorofluorocarbons and being attacked from 2 new unregulated directions. Global brightening from the clearing of industrial aerosols is unmasking warming that has been building for decades. Any one of those observations would justify a scientific paper. Any 2 would justify a research program. The fact that all of them are simultaneously active, all within the same era of measurement, all pointing in directions that each system's own feedbacks will amplify, is something different from any of them individually. These systems are not isolated. The inner core dynamics affect the outer core churning, which generates the magnetic field, which affects the ionosphere, which forms the upper boundary of the electromagnetic cavity. Ice melt drives both the axis shift and the Atlantic circulation disruption. Aerosol changes connect to the surface temperature changes that drive the ice melt. Ice melt connects back to the timekeeping crisis through the rotation rate. The rotation rate connects back to the inner core through the angular momentum chain. The threads do not run in parallel, they loop back through each other. The configuration of simultaneous signals is what is genuinely new. Scientists have measured individual magnetic pole accelerations before. Individual circulation weakenings have occurred before. Individual axis shifts have happened before. Each element in this story has a precedent somewhere in the geological record. What the instrumental record of the past 50 years is showing, and what the past decade in particular has made impossible to ignore, is a co-occurrence of anomalies across physically coupled systems, all active in the same brief window. The critical qualification is that instruments sensitive enough to see all of this simultaneously have existed for only a few decades. The inner core's behavior was inferred rather than measured in real time until seismic arrays became dense enough to resolve it. The Schumann resonance has been monitored continuously for only a few decades. The cold blob south of Greenland required years of satellite sea surface temperature data before the pattern became clear. We are measuring this now. That is the best and worst thing about this moment. Recorded human civilization is roughly 12,000 years old. That is the span from the earliest agricultural settlements to the present. Measured against Earth's timeline, 12,000 years is a single film frame. The planet is 4.5 billion years old. Every written language, every government, every built structure, every piece of infrastructure was created during a single narrow window of what the geological record describes as extraordinary stability. The magnetic field has been at or near its modern strength for most of the past 10,000 years. The period in which agriculture was invented, in which cities were founded, in which the Industrial Revolution created the infrastructure civilization now depends on, coincided almost exactly with a long plateau of magnetic field strength. In the context of Earth's longer history, that plateau is unusual. The field has reversed polarity hundreds of times in the geological record, transitioning through periods of weakness that lasted tens of thousands of years. The most recent full polarity reversal occurred 780,000 years ago. The average interval between reversals over the past few million years is roughly 250,000 years. 780,000 years have passed since the last one. The field is declining. The anomaly is growing. The Atlantic meridional overturning circulation has been in a relatively stable operating state since the Younger Dryas collapse roughly 12,000 years ago. The Younger Dryas was the last time the circulation failed. The collapse plunged the northern hemisphere into a rapid cooling event that lasted over 1,000 years before the circulation restarted. In the 12,000 years since, the circulation has remained in the state that current civilization was built around. Coastal settlements along the northeastern United States, the United Kingdom, and Western Europe are sited in places where sea levels, storm patterns, and temperature ranges are defined by the current circulation regime. Agriculture in the monsoon zones of South Asia and West Africa was established, expanded, and now feeds billions of people under the precipitation patterns that the current circulation maintains. The aerosol cooling and the greenhouse warming partially cancelled each other out from the 1950s through the 1980s, creating an artificially moderated surface temperature window during the same decades when global infrastructure was being constructed at the largest scale in history. Power grids, water systems, transportation networks, and coastal defenses were designed using climatological baselines from those decades. The baselines were real measurements of real conditions. They were also, it turns out, the product of a temporary balance between two large competing forces, one of which has since been partially removed. The window was not manufactured. The stability was genuine. The magnetic field really was strong. The circulation really was vigorous. The temperature baselines really did reflect the actual climate. The insight that the era of measurement is now providing is simpler and stranger. The stability was real, and it was contingent. It depended on conditions that the planet maintains over long periods, with occasional sharp departures, and the departures are now underway. Civilization was built during the calm. The calm was an exception, not the rule. And the scientific frameworks that might tell us where the departure from that exception leads all share a built-in limit on how far ahead they can see. Among the many honest confessions embedded in the scientific literature covering the systems described in this video, the most recurring and the most uncomfortable is a simple acknowledgement of how far the best available models can see. The instruments and frameworks that produced every discovery in the preceding chapters are the most sophisticated Earth science tools ever built. They have revealed things about this planet's interior, oceans, and atmosphere that previous generations could not have detected. And none of them can reliably tell us where this goes. The geomagnetic field's behavior is the clearest case. The same mathematical structure governing weather makes the outer core's turbulent fluid dynamics fundamentally unforeseeable beyond a few decades. Researchers who have spent their careers modeling the geomagnetic field have stated explicitly that the field cannot be predicted more than a few tens of years in advance. The jerks, which arrive roughly every 3 to 12 years and snap the field into a new trajectory, cannot be forecast. The timing of the next jerk is unknown. Its magnitude is unknown. Its direction is unknown. The only thing known with certainty is that it will happen. Every piece of navigation infrastructure that depends on knowing where the magnetic pole will be in the coming decade is operating on a model that acknowledges it cannot see that far clearly. The Atlantic overturning's trajectory has a different kind of uncertainty problem. The 95% confidence interval on the most physically rigorous collapse model available spans 27 years, 2037 to 2064. This range is often described as large, suggesting the outcome is uncertain. The framing gets the interpretation backward. A 27-year window means the model is confident enough in the physics and the trajectory to identify a specific span within a vastly larger range of possible futures. The model is telling us that a collapse is sufficiently well constrained that we can identify the decade most likely to contain it. That is a deadline written in probability, centered on 2050. With the bulk of the probability mass landing inside the remaining lifespan of people alive today. The climate and atmospheric models face a different kind of limit. The precise magnitude of termination shock exposure if rapid decarbonization clears remaining aerosol pollution simultaneously. The exact ozone impact of the rocket launch growth trajectory over the next 30 years. The timing and regional distribution of wildfire ozone damage as fire seasons intensify. All of these sit in zones where projections fan out dramatically, depending on which scenario is fed into the model. The models agree on direction. They disagree substantially on magnitude and timing. In a system where thresholds exist, disagreement on magnitude and timing is not merely an academic problem. The inner core's trajectory presents yet another kind of uncertainty still. The current sub-rotation phase is part of a roughly 70-year oscillation that has happened before without identifiable catastrophe. Whether this particular iteration is meaningfully different from previous ones because of the surrounding context is a question the models can hold but cannot resolve. We know the direction of travel in every system covered in this video. The map shows the road and shows the road heading downhill. It does not clearly show where the slope levels off, and the systems we built during the calm were not designed for the gradient the road is showing. Calibration is the process of adjusting an instrument or a system to match a known standard. A thermometer is calibrated against a fixed reference. A navigation system is calibrated against a model of Earth's shape, rotation rate, and pole position. Every measurement has a reference. Every reference was established at a moment in time. The question that the preceding chapters force is, what were those references calibrated against? And is that reference still valid? The Global Positioning System constellation was designed and its orbital mathematics were calculated using Earth's rotation rate as measured during the 1970s and early 1980s. Every satellite's predicted position at any moment depends on knowing how fast Earth is turning beneath it. The satellites are continuously updated with corrections from ground stations, but those corrections are calculated against a model of how the planet moves. As Earth's rotation accelerates, as the magnetic pole sprints, as the axis shifts, the corrections required become larger and more frequent. The systems work. They are calibrated to a planet that is no longer quite the one that existed when the calibration was performed. The World Magnetic Model, the global navigation standard maintained by the National Oceanic and Atmospheric Administration and the British Geological Survey, is updated every 5 years. The update released for 2020 required an emergency off-cycle revision in 2019 because the magnetic pole had moved so far from where the previous model predicted that navigation accuracy had degraded beyond acceptable tolerances. The emergency update was issued ahead of schedule. The next cycle may require the same treatment because the physics driving the pole's sprint has not changed. Coastal infrastructure presents the most consequential version of this calibration problem. Storm surge barriers protecting major cities were designed using sea level baselines, storm frequency distributions, and tide models derived from historical data. The baselines were accurate measurements of the actual ocean as it behaved during the decades when the measurements were taken. The problem is that those measurements were taken during the stability window described in the previous chapter, the period of relatively intact Atlantic circulation, relatively stable sea levels, and relatively constrained Greenland ice sheet dynamics. A circulation collapse, in the scenarios derived from the paleoclimate record of the Younger Dryas, adds substantial sea level rise along the east coast of the United States because the circulation's natural suppression of coastal sea levels disappears with it. The The storm surge barriers protecting coastal cities in that region were designed without that additional load in the calculation. The drainage systems, the port depths, the coastal engineering specifications all were set during the window that the current trajectory is exiting. The infrastructure is functioning. The calibration is becoming outdated. The baseline used to define normal was a snapshot of a planet that was already, at the moment the snapshot was taken, beginning to change. Everything built on top of that snapshot assumed it was permanent. It was a moment, and what comes next does not require catastrophe to matter. The systems simply need to keep drifting from their calibration points, and the gaps between where the infrastructure was designed to function and where the planet is actually operating keep widening quietly until the gap is too wide to bridge incrementally. Thresholds are the defining feature of the systems described in this video. A threshold is the point at which the same physical mechanism that was previously keeping a system in one state begins, irreversibly, to push it into another. Below the threshold, perturbations are absorbed and the system returns to baseline. Above the threshold, the system reorganizes around a new configuration and does not return to the old one on any humanly relevant timescale. Finding the threshold before crossing it is the entire problem. And the problem is that thresholds are invisible until crossed. The scientific position on all of these systems shares a common structure. The inner core oscillates on roughly 70-year cycles and has done so before without causing identifiable surface crises. Magnetic polarity reversals do not appear in the geological record as mass extinction events. Life continued through all of them. The Atlantic overturning has collapsed before, during the Younger Dryas, and the planet did not cease to function. The ozone layer survived the stratospheric water vapor injection from the Hunga Tonga eruption in 2022, the largest volcanic stratospheric injection in decades. Every single system in this story has precedents for behavior more extreme than what is currently measured. None of what is described here is guaranteed catastrophe. The equally honest position is that guaranteed catastrophe and significant disruption are not the same thing. A temperature change of 10 to 15 degrees across northern Europe within a decade is precisely what the paleoclimate record shows from the last Atlantic overturning collapse. That is incompatible with the agricultural systems, energy grids, and water infrastructure of the 300 million people who live in northern Europe. Infrastructure does not automatically collapse because the climate changes. It becomes inadequate, requiring replacement at a pace and cost that no existing economic or political system has planned for, while the people dependent on that infrastructure still need to eat, stay warm, and be protected from floods. The threshold problem has a specific property that makes it different from problems that scale linearly. With a linear problem, a small additional dose of the harmful input produces a small additional amount of harm. Thresholds work differently. Inputs can accumulate over a long period with minimal visible consequence, followed by a single additional input that crosses the line and triggers the reorganization. The cumulative inputs before the threshold feel manageable. The crossing feels sudden, and the reversal is impossible on any timescale that matters to the civilization that crossed it. Every threshold in this story is invisible until crossed and irreversible once crossed. The Atlantic overturning tipping point will not announce itself. No instrument will display a readout showing the percentage of threshold remaining. The system will show precursor signals of the kind already present in the observational record, and then, in the models, it will cross into a different regime. The gravity anomaly over the Atlantic coincided with a magnetic jerk in September of 2025. The underlying mechanism is still being investigated. The monitoring systems that would distinguish gradual drift from an approaching threshold are only now becoming sophisticated enough to detect the precursor signals. We have instruments capable of telling us we are approaching these thresholds. That is both the most valuable scientific development of the current era and the most vertiginous thing about it. Return for a moment to the seabed off my yacht. A new volcano had been building for months. The magma chamber beneath it was resonating on a 17-second cycle, sending a signal around the globe across 11,000 miles of rock and ocean. Global seismic networks were running. Data was being collected. Automatic detection algorithms were operating. For months, nothing in the professional monitoring infrastructure flagged the signal as significant because the signal did not match the pattern the algorithms were designed to detect. It took one person, sitting at home with curiosity and a live seismic feed, to notice the zigzags and ask what they were. This story is worth returning to because it contains a compressed version of the argument that runs through all 32 chapters. The planet was doing something loudly enough to be detected across the entire globe. The infrastructure built to listen for planetary events was present and functioning. And for months, the event was invisible to that infrastructure because the infrastructure was built to detect a different kind of event. The monitoring gap was a calibration mismatch between the tools and the signal. Every system described in this video has some version of that story embedded in it. The inner core was slowing for over a decade before seismic data accumulated to the density needed to confirm it. The magnetic pole's acceleration became apparent only after it had been moving fast enough for years to outpace the update cycle of the models built to track it. The cold blob south of Greenland was present in the data for years before it was widely recognized as the diagnostic fingerprint of a weakening circulation. The global dimming was measurable for decades before the scientific community had a name for it. The gravity anomaly over the Atlantic was detected in September of 2025, and, as of early 2026, the full explanation has not been published. The planet is communicating. The signals are real, measured, and in the scientific record. The difficulty is that each signal speaks a different language, measured by different instruments, interpreted by different communities, published in different journals. The seismologist studying the inner core was not, for most of their career, in regular conversation with the oceanographer studying the overturning circulation. The atmospheric physicist studying global dimming was not historically in the same conversation as the geomagnetist studying the South Atlantic anomaly. The signals connect. The disciplines measuring them were built separately. What the past decade has begun to produce is exactly that larger conversation. The recognition that the inner core and the magnetic field and the ice melt and the ocean circulation and the atmospheric chemistry are parts of a single physical system, and that a complete description of what the planet is doing requires reading all of the signals together rather than each one in isolation. The Schumann resonance is changing. The inner core is shape-shifting. The magnetic field is weakening, accelerating, and jerking. The ocean circulation is slowing. The atmospheric chemistry is being disrupted from multiple new vectors simultaneously. Every one of these threads started underground, or deep in the ocean, or in the upper atmosphere, decades before the instruments were good enough to see them clearly. Every one of them ends in the same place. Wherever you are, standing on the surface of a planet in the middle of changing its behavior, listening in real time to a conversation that has been underway far longer than the listening. One thread remains. The thread that started everything. 3,000 miles straight down, a ball of solid iron roughly the size of the moon has been slowing. That is where this story began. It is where this story ends. Everything else in the preceding chapters follows from it, connects through it, or echoes it from a different altitude. The angular momentum of that slowing ball moved upward through the outer core and into the mantle and into the crust and shortened your day by fractions of a millisecond. Fractions accumulating toward a reckoning with the timekeeping systems that global civilization runs on. The geodynamo that the outer core's churning produces is the magnetic field that deflects charged particles from the star at the center of our solar system, and that field has been weakening for 2 centuries. And the anomaly at its weakest point has been expanding, and the pole that ships and aircraft and every compass on Earth uses for navigation has been sprinting across the Arctic towards Siberia at twice the speed it moved a generation ago. The ice melt breaking the rotation from above is also flooding the North Atlantic with fresh water and starving the sinking process that drives the ocean's largest circulation system, a system whose precursor signals of failure are now present in observational data. The atmosphere spent 40 years artificially shielded from the full power of the warming building beneath the aerosol layer, and that shield is thinning and the unmasked warming is arriving. While simultaneously the ozone layer is under pressure from rockets below and wildfire smoke above, two sources for which no international regulatory framework exists. The electromagnetic heartbeat of the planet, the resonance that has been pulsing since lightning first struck the early Earth, is being altered by the changing ionosphere, which is itself being altered by the weakening magnetic field, which traces back to the inner core. Every chain in this story begins 3,000 miles underground and climbs to wherever you are. The honest sentence, the one that represents the actual scientific position rather than the dramatized version or the dismissive version, is this: we are watching several of the planet's fundamental regulatory systems shift simultaneously, in directions that are correlated, and our models cannot reliably predict where they go from here. That sentence does not contain doomsday. It contains something more specific and, in some ways, more uncomfortable. Genuine uncertainty about the behavior of systems that civilization was built on the assumption of stability for. The inner core oscillates on long cycles and has done so before. Magnetic reversals do not kill life. The overturning has collapsed before and restarted. The individual elements of this story are all, in one sense, familiar to the geological record. The configuration of simultaneous elements, all active at the same moment, measured by the same generation of instruments, all feeding back into each other, all departing from baselines established during the single most stable period in the relevant measurement record. That configuration is genuinely new. The baseline was not forever. It was a window. Civilization was born inside it. Everything we depend on was built inside it. We are the first generation with the instruments to read, in real time, that the window is moving. The planet is not dying. It has cycled through configurations more extreme than this one and emerged changed, as it always has. What is different now is the infrastructure layered on top of it, calibrated to the window, and the 8 billion people whose ordinary days depend on that infrastructure remaining accurate to the world it was built for. The question is whether the systems constructed during the calm have the flexibility to accommodate the shift. 3,000 miles down, the iron heart of this world is still slowing. The seismic waves from earthquakes, nobody planned and nobody timed, carry the news upward at miles per second through the rock, into the instruments, into the data, into the understanding of people trying to figure out what it means. The planet has been speaking this language for billions of years. We have been listening for decades, and we are only just beginning to hear what it is saying.